Okay, hello everyone, welcome to my channel. This is the fourth video from the projectile motion inside the engineering dynamics series that I'll be doing. Okay, so in this problem, I'll tell you now that it will be a little bit more complicated than the last one. So make sure you stay focused on to the step I narrative I'm giving you. So firstly, let's look on the problem statement on what they ask us to find and what they are giving us. Okay, there is a basketball player. Okay, take a shot from the point shown in the figure. Okay, with velocity about 23 feet per second, about making a theta angle with horizontal axis, and should be released from his position to exactly to the hoop that located 10 feet above ground with 13.75 feet. So that is basically so far what the problem has given us. So they asked us to help this guy determine a possible value from the launch angle data and the time that it needed to travel from his shooting shot to the exactly in the center of the hoops. So far we look at the problem, we're seeing that they used the unit of feet as a distance, and I think we're happy with it because the unit is very much consistent. They use feet per second as a velocity, they use feet at the distance, and they use feet per second square as acceleration in gravity. So we're happy. We don't need to change it or convert any unit here. Okay, the ball is launched from this position shown in the motion just a moment ago. Then let's help this guy score a foul shot to find the angle and the time. Firstly, of course, we could start with any distance. I would like to start with the distance in vertical axis sy. Okay, again we pull out the same equation, s equal to ut plus 1 over 2 at squared, and we should be determining the vertical axis distance and vertical axis velocity here. So distance vertically is 3 feet above the original position that we put the positive 3 here. Okay, and v0 sine theta, because we doesn't know the data, we put the data as the unknown here. Put the gravitational, I'm sorry, the gravitational here should be feet per second square. So we use 32.17 feet per second square here as the unit, and then we plug in the initial velocity of 23.5 here. Then we make some calculation. We left with the unknown of theta and time together. Okay, make it more easily noticed, and we call this one equation 1. Okay, now equation 1 left us with t and t squared and theta, and I'll tell you it will get a little bit more useful once we know the information of another equation. Okay, so to do that, we bring out the sx, the distance in horizontal axis, and also the same old equation, s equal to ut. Okay, so in this equation we plug in the velocity in x-axis is v0 times cos theta here. So we know that horizontal distance from the launch point and the hoop is given to be 13.75 feet. So we plug in here, velocity to be 23.5, plug in here, and then we left us with another equation with two unknown. Okay, so t cos theta equal to 0.58 is the second equation, but you can see that there's some mathematics complicated here. Firstly, the t is not t has a square here. This one doesn't. Second, the data, of course, the same data, but this one is sine, this one is cos. So to solve this one, we have to bring out a little bit more of the mathematical knowledge from the first three questions that doesn't involve in the first three questions. So t squared, I would like to power this equation by power 2 and give us t squared cos theta squared equals to 0.34. That is the reason being is that to convert sine to cos or cos to sine, we bring out the geometry identity, which is sine squared theta, sine theta squared plus cos theta squared equal to 1. This should give us the conversion we need. So to change cos square to sine square, we change cos square into 1 minus sine square. Okay, now we converted cos theta to sine theta completely. Okay, then we do some arrangement or flip equation, and then we got that sine square theta equal to 1 minus 0.34 divided by t square. Okay, so there's some similarity now. Now they're both in terms of sine theta. So we call the equation 2 sine theta equal to plus or minus this term inside the square root. Okay, so plus and minus is when you reduce the square into degree 1. Every time you should put plus and minus sign in front. Okay, so that means because this term could be minus and power by 2, and that minus sign is gone. So that means there's possibility of plus and minus in this term, but don't worry, we can use the plus sign first, and then we will solve later that sine theta may be minus or not. But firstly, I will use the plus sign. Okay, to determine time, we plug in the sine theta for equation 2 inside the equation 1. Okay, now we left with this kind of mathematical terms, and we know that on the right hand side here they have t in front of square root. If we were to put the t inside the square root, the t should be powered by 2. Okay, so t power 2 is going inside the square root, time 1 will be t squared. Then the t squared that multiply in this in this value should cancel out the t squared, and that is at the divider. So we left out with this form of equation. Then we call this one equation 3. Okay, so now combine 1 and 2, left with equation 3. In equation 3, if you look closely, the kind of the unknown, the only unknown we have is t squared. Okay, t squared on the left, t squared on the right inside the square root. So it should give us some idea of how to solve it. I will guide you to the technique I have been observing in this kind of problem. So determine time using equation 3. So we know that, okay, this is the right hand side, the left hand side and right hand side, and you notice that I've left a blank here. Okay, I will show you the technique I learned. So this technique, I minus both sides with the certain constant needed to make a common term in both sides. Okay, so we notice that the t squared minus 0.342 is inside a square root, which gives us a hard time to solve it. So what I did here is I minus the same constant time the coefficient in front of t squared. So you notice that the 16 here is exactly the same as 16 here. Okay, reason I put this so that we can drag out the term here to have exactly the same as this term. Okay, now if you minus something on left, this should be exact same value minus on the right, so that the equation will stay true. Okay, so I combine this here and the green portion here, and drag the common term 16.08 outside. Okay, so the left with t squared minus 0.342. Okay, and we'll left is whatever have left on the right side. Then you notice the exact same term, it exists on both sides of equation, which is t squared minus 0.342. One is not in square root, another one is in square root, but don't worry, we will give this the one in square root as an a variable. For example, a equal to square root t squared minus 0.342. So if this a is powered by 2, it should give us the exact same the value here in the yellow portion. So rearrange equation, you get 16a squared plus 3 equal to 23.5a, which is the square root, minus around 5.5. Then we do some mathematics arrange to be a simple polynomial equation, and we solve that a can equal to two possible values, 0.8 and 0.6. Okay, then we substitute back that a equal to square root t squared minus 0.342, and we will get that this equal to can either equal to 0.8 or 0.65. If we solve this one, t will be equal to 0.9941. Another one will be 0.8795. So there is two possible time that travel that this basketball travel. So that should mean something. So one time could mean one angle. Another different time could be another angle. Okay, have you noticed that if you launch a basketball in a little less angle, so it should require less time. If you launch it in very steep angle, so the projectile would go take a little bit more time to follow through the hoop. So we determine the theta 1 by t1. Here we bring out the equation 2, like I mentioned, plus and minus. Okay, we plug in t equal to 0.99, and we left with the theta, sine theta equal to plus or minus 0.8, and we select positive sine. We will left with 33.96 degree. So reason why I didn't select minus, because the sine theta will be minus in the quadrant, in the fourth quadrant, meaning that the angle instead of this angle will be downward like this, which is impossible to launch a ball to bounce down and expect to go in the hoop. So this positive angle is one answer for T1. Then for the T2, for the theta 2, we substitute T2 here inside. We get that the arcs this should be arc sine. Then the arc sine of 0.74 should be 48. Okay, so like I mentioned, this is very natural that if you launch the angle kind of more less inclined, you will get less time. It will require less time to travel. If you launch it to a little bit more steep, require more time to travel. So 0.99 is more than 0.87. So that kind of makes sense after we solve this one. So that's it. That's the end of this question. Okay, I know this is a little bit more involved in mathematically, but in projectile motion, that is naturally we have to encounter at least polynomial equation. So that's what expect to be in this kind of equation. But I hope you guys enjoy how to solve this one as I am, and thank you again for watching this video. It's mean a lot that a lot of people learning from the video I make. Again, thank you, and see you guys in the next video. Let's stay tuned on what the next problem will be. Okay, thank you for watching. See you.